rate laws and order of reaction. Here, if you look at this reaction, 2NO plus O2 give you 2NO2. The rate of reaction depends on the reactant. Let's say the general, when we have AX plus BYX and Y is your reactant, A and B is the coefficient. Then the rate is proportional to the concentration of the X and concentration of the Y, basically your reactant. And the power of this concentration is M and N. We find this M and N experimentally. So look at that as it's proportional to that, but R actually equal to K, concentration of X power M multiplied by concentration of Y power M. So we call K the rate constant. And it depends on the temperature. Okay, looking at that, when we have this reactions, so the R is equal to K, NO2, concentration of the NO2 and concentration of F2. Experimentally, we will realize that the power of these brackets are 1 and 1. It means the order of reaction with respect to NO2 is 1, and the order of reaction with respect to F2 is 1, and the overall is 2. 1 plus 1 is 2, the overall rate of reaction, order of reaction. Here is another example. We do experiment, we realize that the R is equal to K, concentration of X power 1, concentration of Y power 2, concentration of Z power 0. It means the rate of reaction with respect to X is the order of the reaction, respect to X is 1, respect to Y is 2, respect to Z is 0. It doesn't, when it's like a Z 0 means Z does not have any effect on the rate because any number to power Z is 1. If the initial concentration of Z is double, then the rate of that is multiplied by 1 and will be unchanged. If the concentration of the Y become double, 2 to the power of 2 is 4, the rate becomes 4 times bigger. If the concentration of the X become 2 times bigger, 2 to the power of 1 is 2, so the rate will be 2 times bigger. If the concentration of Y becomes 3 times bigger, how does it affect the rate of reaction? So it's going to be 3 to the power of 2, so it's going to be 9 times the rate of reaction will be 0.5. If the Z become 2 times bigger, 2 to the power of 0 is 1, or 3 times 0, 3 to the power of 0 is 1, so it means it won't affect the rate of reaction. Means overall rate of reaction is just K, X power 1, Y power 2, because the Z power 0 is 1, doesn't have an effect. All right, here, look at this question. The decomposition of the dinitrogen pentoxide is given the first order with respect to N2O5. Means the R rate of reaction is K N2O5 to the power of 1 because it's with respect to N2O5. The order is 1, the first order means the power is 1. If the initial rate concentration is given, so the rate is given to you, this R, when the initial concentration of N2O5 is 0.4, concentration of N2O5 is given, predict what would be if the another experiment were performed in initial concentration is 0.8. Now, knowing the rate of reaction and concentration of N2O5, we can find K. After we can find K, then you can put NO2O5 to concentration of that to be 0.8 to find what is the rate of reaction. Okay, so the dimension, okay, so this is an example. The dimensionization reaction of 1,3-butadiene is 2C4H6 give you C8H12. In second order with respect to C4H6. In second order with respect to that means C4H6 to the power of 2, second order. R is K multiplied by that. It said if the initial rate is given, so R is given 32 millimole per liter per minute, make sure pay attention to this units. At a given initial concentration of the C4H6, what would be the initial rate of reaction if the initial concentration were doubled? So if this is doubled, of course, 2 power 2, it will give you 4 times bigger, right? If this becomes 4 times bigger, it's just simply multiply this one by 4 to get the rate of the reaction. Here is another example. When aqueous boromate and bisulfide ion react to produce boromine, the overall equation is given. So here is it. Consider the series of experiment recorded in table 2 in which initial reactant concentration are very varied and rate are compared. From the evidence provided, determined a rate equation. So the thing is that here is the rate, here concentration of HSO3, concentration of BRO3. Okay. Overall, I have this. R is equal to K, BRO3, concentration of that to the power of M, because the BRO3 is your reactant. Which call HSO3, concentration to the power of N. Here is HSO3 is your reactant. Now I'm using one of the two of that. So I use the one that they have the same concentration. C6 and 6 have the same concentration. So I use 1 and 2. So maybe I just put that here, or equal to K BRO3 power of M and HSO3 the power of N. So R for the first one is 1.6. Here is K. The BRO3 is 4 to the power of M. HSO3 is 6. You see, 6 to the power of N. And the second data is 0.8. It's 2 to the power of M here. Six to the power of N. If we divide both sides, so 1.6 divided by 0.8 is 2. K divided by K, it will cancel. Here you have 4 divided by 2 to the power of M. Also, N and N, 6 power and X are divided by each other, it's 1. So from here, 2 is equal to 2 to the power of M. Both sides have the same base, so the power should be the same. So M is equal to 1. Okay. Now we do the same thing, but this time I'm going to find something that the BRO3 is the same, because I use this too for HSO3 to be the same. So the second one and the third one is good. They have the same of that. So again, R of that is 0.8. 0.8 is equal to K. BRO3 is 2 to the power of M. And here is 6 power of N. Here is the rate is 0.2 equal to K. 2 power N. Here, 2 power N, and then 3 to the power of N. So 0.8 divided by 0.4, 0.2 is 4. K divided by K is 1, 2M divided by 2M is 1. 6 power n divided by 3 power n is 6 divided by 3 to the power of n. So 4, you can write it as a 2 to the power of 2. 6 divided by 3 is 2, so it's 2 power n. Since the bases from both sides are the same, the powers should be the same. So n is equal to 2. The power is the same. So I got m and n. Now I'm going to find k. I can use one of this information to solve for k. Maybe last one. So 0.2 is your rate equal to 2 to the power of m. We got m to be 1. And then 3 to the power of n. We got n to be 2. Here, I forgot to put k. So k here. So k is equal to 0.2 divided by 2 divided by 3 power 2. So just use your calculator to find the k to be 1.1 10 power 4. And then you have to write down the log. See, instead of k, you put that number, BrO3 to the power of 1, HSO3 to the power of 2. So the overall rate of reaction is 1 plus 2 is 3. Here is another question. Mixing an acidic solution containing iodate IO3 ion with another solution containing. So this is the reaction we have. So we have a 3 reactant. When you want to write the rate law, so it's going to be RK IO3 to the power of A, I negative to the power of B, H to the positive to the power of C. So basically these 3 to the power of A, B, C. Now we need to find out the rate laws. So the same thing I did in the previous examples. We find the one that have the same. See, for these two and these two are the same. So I take 1 and 2 to find the power A here. I'm going to do it. I'm taking these two. So the rate is 5. 10 power negative 4 equal to. Here, 0.1 is K, we have K. 0.1 to the power of A. 0.1 to the power of B. And 0.1 to the power of C. The second one, we have 1 10 power negative 3 equal to K. 0.2 to the power of A. 0.1 to the power of B. 0.1 to the power of C. Again, we divide this. 5 divided by 1 is 5. 10 power negative 4 divided by 10 power negative. So the overall of these divided by that is 0.5. So K divided by K will go away. 0 point divided by that's going to be 1 over 2 to the power of A. This divided by that is will cancel. This divided by that cancel. So as you see, 0.5 is 1 over 2 equal to 1 over 2 to the power of A. Both sides of the base are the same, so equal the powers. So here is 1. I got A. Then I can choose the other one. See, these two are the same. This and this is the same, and these are different. So if I use these two, I do the same thing. I divide it. I can find B, right? Also, if I use this and this is the same, this and this is the same, then these two are different. So if you use the 3 and 4, do the same thing, I can solve for C. And the same way when I have A, B, and C, I use one of the information to solve for K, the same thing I did in previous example. I want to all of the students go over that solution and do it and check the answer. So for the practice, you do question number 3 and 6. So relating reaction rate to time. Okay, when we're talking about the half-life, what is the half-life? Half-life is if you have the decaying, say decaying start like that. At the beginning, you are 100%. The time it reached the time when your material decayed to the half of the original, 50%. We call it T of half-life. Or sometimes we call it H. So the equation for the half-life is A, amount at time T, equal to A0. A0 is initial amount, half T divided by half-life. Instead of the T1/2, I put H. H is the period that, or the time that it takes for material to decay to half of its original. So you have that. You have here is another one that related the rate constant into the thing. So K, the rate constant multiplied by half-life, is equal to 0.693. The radioisotope lead has a half-life of 10.6 hours. What is the rate constant? But easy, K multiplied by T half is that. So you have half-life, which is 10.6 hours. You just sub that in and you will have a rate constant K. If the mass of an antibiotic in a patient, what mass of antibiotic will remain after 6 hours if the half-life is 2 and no further drug? So what can you do? You can use the equation A is equal to A0 1/2 T divided by H. H is half-life. So the mass of the antibiotic is the initial mass is 2. What mass antibiotic will remain after the 6 hour means I'm looking for A amount after time T. A0 is 2.464. Like we have, the time is 2 hours. Sorry, the time is 6 hours. Half-life is 2. There's 1/2 to the power of 3. Okay, that's 2.464 multiplied by 1/2 to the power of 3. You use your calculator, you'll get 0.31 gram. Because this is in gram, so that the answer will be in gram. Okay, so to practice, you can do question number 7.